Hi, I'm Bob. I'm one of 6 million people in the world who are severely hearing impaired. In a person with normal hearing, sound waves pass through the auditory canal and vibrates the eardrum. The eardrum passes the vibrations through the ossicles to the cochlea. Within the cochlea, there is a body known as the organa corti, which houses thousands of tiny hair cells. These hair cells change the mechanical vibrations into electrical signals that are then sent to the brain through the auditory nerve. Unfortunately, the hair cells within my cochlea are damaged, but luckily my auditory nerve still works, so I'm going to talk to my doctor and get a cochlear implant. Hi, I'm not sure how cochlear implants work. Can you please recommend one for me?
Of course. When you get a cochlear implant, we put a microphone behind your ear which picks up sound. A sound processor, worn behind the ear or on the body, captures sound and turns it into digital signal. The sound processor has a battery that powers the entire system. The sound processor transmits the digitally coded sound through the coil on the outside of your head to the implant. The implant converts this signal into electrical impulses and sends them along the electrode array placed in the cochlea. The implant's electrodes stimulate the cochlear's auditory nerve, which then sends the impulses to the brain, where they are interpreted as sound. Cochlear implants are tonotopically mapped. This means the position of each electrode within the cochlea corresponds to a particular frequency range. Low frequency or high-pitched sounds are able to penetrate into the apex of the cochlea and stimulate the electrodes at the apical region. High frequency or low-pitched sounds cannot pass through the inner walls of the cochlea and instead stimulate the electrodes found in the basal region. Sound is processed within the speech processor according to different strategies. I think the first one we should try is F0, F1, F2. Speech contains resonant frequency bands known as formants, which characterize the sound. If these formants can be extracted and analyzed, the essence of the sound can be deduced. The F0, F1, F2 strategy extracts the first formant, which typically exists between the 300 to 1000 Hz range, and the second formant, which is between the 1000 to 3000 Hz range. The frequencies of the first two formants contain sufficient information for the recognition of vowels from which some words can be deduced.
Awesome! I'll get that.
Bob goes home to watch some TV with his new formant-based cochlea.
I find your lack of faith disturbing.
I could barely hear a thing.
I think you may need a different coding strategy. How about cis? For each frame of sound, the signal is passed through digital filter banks with frequency-specific profiles known as bandpass filters. By applying full-wave rectification and low-pass filtering, the envelope of the filtered frequency bands can be extracted, which can be used to determine the amplitude of each pulse. The envelope outputs are compressed and then used to modulate biphasic pulses, which are delivered to the electrodes to electrically evoke hearing.
Bob tries to watch some TV again with his new cis-based cochlea.
I find your lack of faith disturbing.
The cis strategy works great. I can understand about 75% of what people are saying.
But suddenly, everything goes quiet.
Damn, my implant just ran out of power. Is there some way we can make it last longer?
We can try the speak strategy. In the speak strategy, the incoming signal is sent to a bank of filters, where it estimates the outputs and selects the ones with the largest amplitude. The number of maxima varies, but generally 5 to 10 are taken depending on the spectral composition of the input signal. The electrodes corresponding to these highest amplitude frequencies are then stimulated to produce sound.
I was really impressed with the quality of SIS. Will this be any worse?
Well, a study was conducted with 3 individuals who had no hearing deficiencies. 100 sound files were processed using the 3 different sound processing strategies, F0, F1, F2, Speak and SIS, which were simulated using MATLAB. The study coordinator, an untested individual, prepared the set of encoded sound files and played each one to the subjects individually. The coordinator asked the subject to repeat what was understood from the sentence, and recorded whether or not the sentence was identified correctly, along with the number of words identified correctly. Finally, the original unprocessed form of the 100 sentences was played, and the coordinator recorded whether or not the sentence was recounted correctly by the subject. The histogram on the left compares the sentence recognition for the 3 processing strategies, while the histogram on the right compares the word recognition. 2-tailed t-tests were performed to determine whether SIS and Speak performed significantly better than F0, F1, F2 on mean sentence and word recognition, when a significance level of 0.05 was chosen. For mean sentence recognition, both SIS and Speak significantly outperformed F0, F1, F2. However, SIS and Speak were not significantly better than each other. For word recognition, both SIS and Speak again significantly outperformed F0, F1, F2. However, SIS and Speak were not significantly better than each other. So in short, with Speak, you should still have a similar level of speech recognition as if you had SIS.
Bob tries one last time to watch some TV with his new Speak-based Cochlear.
You call that a knife? This is a knife.
That's not a knife, that's a spoon.
All right, you win. I see you've played knifey spoony before.
Awesome! I can still understand about 75% of what people are saying, and the power lasts even longer. I can now talk on the phone with my girlfriend as well. Losing my hearing sucked, but with these sound processing strategies, I can live a normal life again.
Thank you for listening. This presentation was created by Alex, Lyndon, Tom, and Ching.